everyone! Good day! I am Irma Jane Pagara. In this video, I will be explaining and giving some examples to the following learning objectives. So first, delineate between isomorphism, homomorphism, and automorphism. Second, write solutions to problems involving homomorphism. And lastly, third, articulate proofs for theorems and other claims about homomorphism. So, let us begin! Now, let's start with our first objective, to delineate between isomorphism, homomorphism, and automorphism. Isomorphism, homomorphism, and automorphism are concepts that arise in various branches of mathematics, including algebra, group theory, and graph theory. While they are related and share some similarities, they have distinct meanings and implications. Let's delve into each concept. Let's have first the isomorphism. Isomorphism refers to a structural correspondence between two mathematical objects that preserve certain properties. In other words, if two objects are isomorphism, they possess the same essential structure, even though they may differ in their specific elements or representations. In algebra, an isomorphism typically relates to algebraic structures, such as groups, rings, or fields, in a way that preserves the underlying operations and their properties. For example, two groups are isomorphic if there exists a bijective map between them that preserves the group operation, identity element, and inverses. In graph theory, isomorphism pertains to the correspondence between two graphs such that their adjacency and relationships and connectivity patterns remain the same, despite possible differences in vertex labels or arrangement. Now, homomorphism, like isomorphism, establishes a relationship between two mathematical objects. However, unlike isomorphism, a homomorphism does not necessarily require a one-to-one correspondence between elements or structures. In algebraic structures, a homomorphism is a mapping between two structures that preserves in the operation of the structures. More precisely, if we have two algebraic structures A and B, a homomorphism from A to B is a function that preserves the operations defined on A and B. For example, in group theory, a homomorphism between two groups preserves the group operation. It maps the product of elements in the first group to the product of their images in the second group. In graph theory, a homomorphism between two graphs preserves the edges and adjacency relationships, although it may not preserve the exact structure or labels of the vertices. Now, the automorphism is a special type of isomorphism that relates an object to itself. It represents an isomorphism from an object to itself, where the object retains its overall structure and properties. In other words, an automorphism is an isomorphism that acts as an internal symmetry of an object. In algebra, an automorphism of a structure such as a group, ring, or field is an isomorphism from the structure to itself. In the context of group theory, an automorphism is bijective map that preserves the group operation, identity element, and inverses. In graph theory, an automorphism of a graph is permutation of its vertices that preserves the adjacency relationships and connectivity. To summarize it, isomorphism relates two objects while preserving their structure, while homomorphism establishes a mapping between two objects preserving their operations. And automorphism is a special case of isomorphism representing an isomorphism from an object to itself. These concepts are fundamental in many areas of mathematics and have wide-ranging applications in various fields of study. Now let's proceed to the second learning objective, to write solutions to problem involving homomorphism. So let's have the problem number 1. Given two groups G and H, prove that a function f is to G to H is a homomorphism. We have the solution. To prove that F is a homomorphism, you need to show that for any elements A and B in G, F times A times B is equal to F of A times F of B, where the multiplication denotes the group operation in G and H. You can do this by explicitly calculating the left and right sides of the equation and showing they are equal. Let's have the problem number 2. Find the kernel and image of a given homomorphism F is to G to H. Now, for the solution, the kernel of F denoted by curve F is the set of elements in G that map to the identity element in H. To find the kernel, you can solve the equation F of G is equal to E underscore H, where E under H is the identity element in H. The image of F denoted by Im of F is the set of all elements in H that are obtained by applying F to elements in G. To find the image, you can calculate F of G for all G in capital G. We are now down to the third and the last learning objective, to articulate proofs for theorems and other claims about homomorphism. Theorem 1. Let G and H be groups and let phi is to G to H be a homomorphism. Then phi of E under G is equal to E under H, where E under G is the identity element of G and E under H is the identity element of H. We have the proof. Let G be an arbitrary element in G. So we have phi of E under G is equal to phi E under G times G. An identity property of groups is equal to phi E under G times phi G, and that is the homomorphism property. And that is equal to E under H times phi of G, and that is the identity property of groups. Since this holds for any G in G, we conclude that phi of E under G is equal to E under H. Now for the next theorem, let G and H be groups and let phi is to G to H be a homomorphism. The kernel of phi denoted by ker phi is a normal subgroup of G. So we have the proof. To prove that ker phi is a normal subgroup of G, we need to show that for any k in ker phi and any g in G, we have gkg to the -1 or gkg inverse in ker phi. Let k be an arbitrary element in k phi. This means phi of k is equal to E under H, where E under H is the identity element of H. Now, let G be an arbitrary element in G. So we have phi of G k G inverse is equal to phi of G times phi of k times phi of G to the power of -1 or G inverse. And that is the homomorphism property is equal to phi of G times E under H times phi of G inverse times phi of k is equal to E under H. Is equal to phi of G times phi of G inverse, the identity property of groups, is equal to phi times G, phi of G times G inverse, the homomorphism property, is equal to phi of E under G, that is the inverse property of groups, and that is equal to E under H, the theorem 1. Since phi of gkg inverse is equal to E under H for any G in G, we conclude that gkg inverse is in ker of pi, proving that ker phi is a normal subgroup of G. So, that's it! I hope that you have learned something. Thanks for watching! Bye!